Welcome to LLM Engineering. We're going from foundations to small language models in this class in just 6 weeks. And today we introduce the topic, we introduce AI Makerspace to everybody. Some of you know us, some of you don't. I see some familiar faces in the room, and I also see some new faces. Welcome, everybody. One thing to consider as we kick this thing off is a simple question. Why are you here? What is it that you're trying to accomplish? What is it that you're aiming at in 2025 that led you to think this stuff was going to help you get there? That truly understanding what's going on inside of an LLM is going to give you a competitive advantage. Well, I'll tell you why you're here. Because you guys, all of you, are already well ahead of the LLM curve. We have seen a lot happen in the last year. The State of the AI report just came out, and I got to say, Wiz and I were both kind of like, okay, yeah, those things did happen. If you've been following our stuff, if you've been paying attention to the edge, if you're here, you're already ahead of the game. So, hell yeah. Welcome, everybody. Welcome to AI Makerspace. You know, for 10 years as a university professor, I saw that the only people that were succeeding in a 21st century workforce were those that were learning new skills, using those new skills to build awesome things, and then sharing the awesome things they built with others. It wasn't about degrees or prestige or pedigree or PhDs, right, Deb? It's not about that. It's about building, shipping, and sharing. It's about making stuff as part of a community with other people that enjoy making the same stuff. And it's very simple. This is the key to success as AI becomes more and more prevalent, as automation starts to really affect the entire world. At AI Makerspace, we're on a mission to create the world's leading community for people who want to build, ship, and share production LLM applications. The kind of production LLM applications that create real value for individuals and for companies. Those are the ones we try to educate people about. The secret sauce, of course, is building, shipping, and sharing. It really is that simple. We try to make it easy for everyone to do that and hope that you will also try to make it easy for those further behind down the path. By giving first all of the knowledge that we can possibly muster and always focusing on what we don't yet know over what we already know, this is the ethos. And, you know, it's been really great over the past couple of weeks and months because we've traveled a lot. We traveled last week to Austin, and we got to meet a ton of amazing AI Makerspace community members in person. It was really awesome. Some of them are in this very room right now. What's up, Sahar? And, you know, it's just been so cool to see folks and watch their journeys evolve. Shout out to Deb, who's one of our peer supporters you'll meet today, who just launched her startup, I believe, still without a LinkedIn page, right, Deb? And we met Deb over a year ago now. And it's just been really cool to watch people evolve. People like Mike C., who we met, who's been a peer supporter, who we've met at hackathons. Now he's publishing blogs for Box, for Llama Index, and he's trying to get YC money for his startup, PureML, that he stumbled into at the hackathon. People like Gilberto, who shipped finally and shared finally something after attempting to take the AI engineering bootcamp twice, and he's finally out there getting after it. His first series of blogs is on the path here. And this is all stuff that just got announced this week, and it doesn't stop there. We see folks like Christos that we've known for years really starting to make some moves. Love to see this. We see one of our earliest adopters. You may have seen him on LinkedIn. His name's Harpreet, and one of the original build ship sharers, crushing it harder than ever this week. We all have new mountains to climb all the time. Practiced his big talk with us in the community Discord. That was pretty awesome. And new folks coming in every week, all the time. New folks like Evelyn, ETH. Let's go. If anyone wants to collaborate on this federated learning, you know, hit them up. Hit them up. You never really know on Discord. AI by AI has been working on an avatar program that he then integrated with Notebook LM, and now he's doing vodcasts, video podcasts, fully. Really cool project. Updates all the time in Discord. Or this guy that came into our weekly Monday meeting this week, and he's like, I've been a video game designer my whole life, and I got super into AI, and I fell down the YouTube rabbit hole, and I found you guys. Now I'm just jumping into the Discord. Like, let's go. More importantly for you guys, shout out to, is this Nalay? Is that who this is? Shout out to NJ Havery for, okay, this is what we want to see. We want to see you guys posting in the Discord, living it out, not just building in a vacuum, but sharing it. And you can share it with your cohort. You can share it with the Discord. I love to see, and I want to see more and more of you guys sharing the work that you're doing in the course. There's a lot to be proud of in here, even though you're surrounded by people that are more expert than you are. And by the way, every Monday, I kick off every Monday, 9 a.m. PT in the public Discord. You can find me there with a group of other builders, shippers, and sharers to tell you what they're going to build this week and what they built last week, what to expect from them. So welcome to the community. Welcome to AI Makerspace. Welcome to LLM Engineering Cohort 3. I'm Dr. Greg, and I'm obviously joined on stage a lot of times with the Wiz. But you might not know that actually Sriracha's there with us all the time. She's always there. And she's always there in the background. She's always there helping make sure our productions go off without a hitch. So really, it's always the Dr. Greg, Wiz, and Sriracha show. Lusk is another member of our team. He's unable to join because he's doing some family stuff tonight. We told him, yeah, go ahead and jump in on Tuesday instead. You'll hear from the Wiz today. You'll hear from Sriracha. They already have, I think, right? Most of them. And you'll get to know all of us along the way. But it's not just us. It's also your peer supporters. This is one of the key things that makes AI Makerspace courses different. Makes them, I would say, better. And makes them, hopefully, ones that you can develop much more meaningful relationships in. You're going to be part of a journey group. You guys are going to go on this journey together. And we're going to work hard to make sure that you're paired together with people and with a peer supporter that is at your level and slightly beyond your level of expertise. So you can always be pushing, and we always have this nice community vibe every time we go to a breakout room. Everybody hates those black hole breakout rooms. We don't like them here. You don't have to turn your camera on necessarily, but we want you to engage the way that you want to engage with the course. Speaking of the course, 10 minutes in, it's time we align our aim to the day. Now, today is going to feel sweeping. It's going to feel like so much because it really is. There's a lot to take in. By module and by week here, we have the setup that we've chosen for this reboot of LLM engineering. In the first module, where we're going to spend quite a bit of time, this starts on Tuesday, we're going to talk about the transformer. We're going to talk about the attention mechanism. We're going to talk about the transformer as written, that is BART style, BERT style, GPT style. We're going to talk about what those acronyms mean. And then we're going to talk about attention as originally formulated. We're also going to go further. We're going to talk about flash attention. We're going to talk about flash attention 2. We're going to talk about stuff that's actually meaningful today. Now, it's important to take a moment and an aside, really a whole session to talk about embeddings, because embeddings are really important and they're really confusing, because you'll notice we can talk about embeddings in module 2 and then in module 1, and then in module 2 we'll talk about embedding models. Turns out embedding models and embedding layers, they're not the same thing, even though they kind of are. This disambiguation of language is core to what we have to deal with out on the edge all the time. So you guys know that already, and hopefully you're buckling up for this. And it turns out there's a lot that goes into next token prediction. There's a lot that goes into the details of this. So it takes a while to kind of build it up. Now, fundamentally, when you start playing with models yourself, and when you start training and tuning models yourself, you're not necessarily going to be hard coding some of these things down at the model level. However, the tools that you pick up, the methodologies they use, the way they actually work will be paying attention to these issues. If you want to, let's say, inference a model really fast, you have to kind of understand exactly what's going on with next token prediction, how decoding is taking place, how we're actually leveraging either the full set of weights or maybe a slightly smaller version of the weights. And there's different methods we can use to approach these kinds of problems. These kinds of problems that are going to be problems that we take care of before we go to production. And then, of course, there's a lot of frontier stuff happening, from mixture of this, that, and the other, experts, agents, and judges, to new model architectures. Let's not even go down that rabbit hole, just briefly touch on it. To model merging, used to be just hacker's paradise, and now it's like a legit thing that enterprises do. To distillation, how we're taking the big, bad 400+ billion parameter models and actually just crunching them down. And more all the time, right? More and more all the time. But this course is about the fundamentals, and today is about kicking it off. That's what today is about. You know, one of the things we like to do is we like to define words, because nobody has a good enough definition yet. Our flagship course is called AI Engineering. And this was a little problematic because LLM engineering and AI engineering can be confused quite easily if you don't yet know. AI engineering is that set of skills that teams need to build, to deploy, to operate, to improve LLMs in production. Very important, very enterprise grade, very much the thing that's going to get you one of the many jobs that exist out there. Now, this is not this class, okay? That's not what we're doing. We are doing LLM engineering. We're going inside. Instead of using the API, we're going inside the API. We're trying to understand what's happening in the model that we're doing inference on and why. This is the emerging set of best practices and tools for pre-training, for post-training, which is a huge word, and optimizing, which is an even bigger word. It's like the meta word. LLMs prior to production. Okay. So let's just think about that for a second, and then consider the way that the thought leaders are talking about this stuff. The thought leaders building models, not NVIDIA, all the people out here. How do they talk about it? Well, let's consider Anthropic. Anthropic is probably number 2 to OpenAI. And Dario, their CEO, was on the Lex Fridman podcast. Lex, of course, used to be an expert on AI when he taught AI at MIT, but that was years ago. If you listen to the podcast, you'll realize Lex doesn't quite understand because he's a podcaster now, and he doesn't spend all of his time with AI. The edge shifts so quickly. Let's take a look at what Dario says about models and how they're trained. When Lex asked about the training, he said, yeah, there's different processes, right? There's pre-training, which is kind of the quote normal language model training. And like it takes a super long time. How long? Well, months and maybe many tens of thousands of GPUs. This is kind of the way we've visualized this, especially classical LLMs like early GPT models. There's an unsupervised pre-training step, followed by a supervised fine-tuning step, followed by RLHF. So clean, 1, 2, 3, bada bing, bada boom. However, he goes on to say that then there's this kind of post-training phase where we do reinforcement learning from human feedback, as well as other kinds of reinforcement learning, other kinds. Interesting. That phase is getting larger and larger. And often it's definitely a bit wishy-washy. It takes a lot of effort. It takes a lot of effort. And then it takes some time to get the model working. So we can all hit it, and it works fast, and it works good. And when we hit the API, it gives us back something that's aligned with our expectations, that's following instructions, that's not too harmful, that's going to give us exactly kind of a good vibe, and that's going to obviously do inference fast, at least fast enough so that if we're doing real-time kind of token spitting out, we can read it at a comfortable pace. And there's a lot of steps here, both in post-training and when we go to inference. Now, Lex follows up. He says, well, what about the RL preference data you have, the stuff you get from humans? Can you kind of loop that back in and use it as pre-training again? And it's like, well, yeah, of course. You can make post-training kind of pre-training. You can use preference data from the old models and use it on newer models. For sure. And like, by the way, we don't just do RLHF. We do this other thing that Anthropic came up with. It's called constitutional AI, where they don't use preference data. Rather, it's a post-training process where the model is kind of, quote, trained against itself. And then there's new types of post-training the model against itself that are used every day. That's a key line there, that only by the end of this cohort will you really have some intuition on. New types of post-training the model used on every day. What is constitutional AI? Well, we've talked about it elsewhere, but the AI gets a constitution, right? That's what happens. You know, something like this, although not quite this. It usually looks more like this. Be polite, you know, point out harmful, problematic, age inappropriate, legally questionable stuff. Don't do bad stuff. Be good, like we want humans to be, right? So it's not just RLHF. There's a bunch of other methods as well. Post-training, very important to pay attention to. Now, keep in mind, post-training was not a word when we taught this 1 year ago. Let's see what the small language model people are saying, because we just talked to them. We talk to them quite often, RCAI. Their whole thing is about small language models. Their whole thing is about merging and training SLMs, merging and training. So they just released a new SLM, a 70 billion parameter SLM, small language model. That's called Supernova. Now, Supernova is a distilled version of Llama 3.1 405B instruct. Distilled version. Well, distillation is one of these post-training techniques out on the frontier. So they took the 405B and they just, that sounds pretty sick. But that's not all they did. In fact, we talked to the researchers that actually did this on YouTube, and they said, well, we actually trained a few other models using standard supervised fine-tuning. We did some direct preference optimization, an alignment technique similar to RLHF, although doesn't use RL. And then we merged all the models at once. So you're kind of left with like, huh? You know, what? So let's see if we can recap. So Anthropic said, we use pre-training, we use RLHF, we use constitutional AI, aka RLAIF, we use other post-training techniques, and we're keeping track of other post-training techniques all the time. RC Supernova, they said, well, we took Llama 405 instruct 3.1, and then we distilled it down. And then we fine-tuned a few other models, we did some DPO on another one, and we merged all of them into Supernova. And we were talking to the guys, and these are guys that like just finished their master's and PhD, like at the right university lab in the right thing at the right time, right? These are like guys that are like on the, you know, getting paid to actually be on the edge. That's their job, is to sit and think about the edge. And we were like, well, if somebody were to start out and try to learn this stuff, what order should they learn it in? And here's what they said. They said, well, they should use SFT first, then DPO, then merging, then distillation, and then maybe get into continued pre-training. Because it turns out, you know, not all of us are going to do pre-training because it takes many tens of thousands of GPUs, many months. And, you know, that's why these companies have to spend billions of dollars. Now, a few more notes just to keep in mind here, just to contextualize this more fully. When we talk about pre-training, one of the things that's happening is we have three levers. We can have more parameters, more weights, bigger models. We can train them longer, or we can use more data. And it's kind of fun that not too long from now, we'll kind of run out of data generated by humans that we can train this model on. So if you take all the data from the internet and use it, what do you do then? Well, you got to generate more data synthetically. In order to keep scaling, we need more. Bigger models, more data, train longer, and we get better. We don't know how far this goes, but we think it goes pretty far. Well, some people do. And of course, then there are this idea of small language models, that when it came out, this was a 1 billion size model. Things like tiny stories and textbooks are all you need, sort of led the way here. But now we have 70 billion small language models. Now, keep in mind, we want to look for the core principles. We don't want to get confusing. We want to be fundamental in this class. And so when we talk about LLMs, when we talk about SLMs, these are all just GPTs. They're generative pre-trained transformers. This was a fun quote from Ilya Sutskever this week, who obviously he left OpenAI, big hullabaloo, and then he started his own, I think it's Safe Superintelligence. That's the name of the company. And he talks about scaling the right thing matters more than anything else. Here's a little prediction for you. As we have definitions, we also have predictions. So, you know, if you come back in a year and you want to learn LLM engineering again, we can maybe start to compare these things. Synthetic data is going to play a larger and larger role. And one of the things that we're looking at in 2025 is that models that are trained on actually synthetic data are likely to start outcompete non-synthetically generated data trained models for specific tasks. And if we kind of zoom out one more level, because it's kind of fun. This is my favorite from the State of the AI report. Attention is all you need to raise billions to sell your AI startup. All of the folks in this paper that, by the way, your homework before Tuesday is to read this paper as a once through. They've all done really cool stuff. And it's worth paying attention to what they've done as much as it's worth paying attention to where it all started. All right, so Wiz, you know, we talked about this obviously this week. LLM Engineering 2022, a little bit different than LLM Engineering 2025, right? I believe you said, and the quote is LLM 2022, collect data, train model. LLM 2025, more like generate data and train model. I mean, how do you make sense of this crazy world that we're living in where there's, you know, 16 different processes to get a model ready for production? And what do you expect from LLM engineering moving forward?
Yeah, I mean, the big things or unlocks are, I think, pretty clear, right? So it's getting easier to train models. We're figuring out kind of the best ways how to train models. That doesn't mean from a data perspective, it means from a, you know, algorithm perspective, or how much of the model do we need to train, or you know, what are we actually trying to do with training even? You know, all these things we're exploring extremely quickly now. And I think as we continue to evolve, you know, LLM engineering is going to be, first of all, way less time pre-training. I think pre-training is already, you know, falling by the wayside for a lot of companies that are actually trying to create like value from models, and a lot more time adapting models that we already have, thanks to shops like Meta. The quote someone put, like, Mark Zuckerberg is like the open source messiah or whatever. Like that, that's super
De
true.
facto open source messiah.
Yeah.
That's right.
It's super true, right? Like it is something that, because it enables us to spend more time creating things of value. Uh, I think LLM engineering is going to quickly become tinkering with an existing pile of weights to get it good at the task you want, or combining or merging, a suites of models to perform very well on specific benchmarks that are related to your business use cases, and way less on pre-training. I think pre-training shops are kind of already spinning away. They're doing their thing. They're gonna keep cranking out models, and
right.
we get to reap those benefits by proxy. I also think that one of the big things that's going to help us is, thanks to shops like RC, who are very focused on making sure that these techniques that we're using continue to be useful for as long as we stay in the transformer architecture. So as new models come out, we can very quickly redo the things that we did the last time. I think these efforts are going to help us stick with the same set of tools. So insofar as we don't have some massive algorithm change. So future's looking bright, but definitely, it's going to be different in a year than it was, just as we saw last year. It's going to be, we're going to approach the whole field a lot differently as we move through 2025.
Yeah, and I think, when you see these people that try to go create their own models, and then most of them flop now, and it's like you still see the leaders out there, still raising tons of money, and the money's just going straight to compute, and it's like that's a thankless work game to be in that position of building and doing the pre-training. But yeah, like if we can leverage, basically, like, I think we were talking about the RC's entire business model is take Meta's newest open source model and do something great with it. And I think that's going to be the business model of a lot of startups heading into 2025. And they're going to be doing it through this engineering of the actual LLM. And although this isn't a job, title you'll find often today, it's a bit more researchy in nature today. I think it is going to be something that does get, as companies scale out, and they're, every company has 5,000 different models for different things. You're going to really be personalizing those models, and you're going to need people that are really, really good at doing it very, very quickly. And so, I'm really, really excited about the future. I'm excited how this intersects AI engineering, and I'm excited about being able to walk through this. So with that, everybody, just note that all the stuff we just talked about, that's like a practical level, occurs later in the course. Okay, so, but trust us, it is practical to know this stuff when you start talking about, for example, inference optimization. You want to know about the KV caching, which you will have to know about attention for. You want to understand, well, what embedding model should I pick when I'm building a RAG application, for instance? Well, if you know about how embedding models work and exactly where they come from, it makes it a lot easier to feel pretty confident in those things. And to really understand how to put guardrails on something, to understand the decoding process and next token prediction is so fundamental. And not to mention the whole optimizing of LLMs for inference at the end, once you finally get them, that sort of is right at that edge between LLM engineering and AI engineering. We're going to do a quick rapid fire course overview. So this should be quite a lot of fun and give you some more kindling for the discussion fires in your peer supporter rooms that will mostly end on before we wrap today. But we've got quite a bit that we want to kind of walk through. Now, we can't walk through everything, obviously, because it takes 6 weeks. And even then, we're really kind of just giving you trailheads. But I want to give you some key points that are going to help you kind of with the homework and help you contextualize the demos today. So we're going to go from sort of 0 to small language model O1 reasoning in 25 minutes. Okay, this diagram right here is mid. If you don't know, what mid means, you will by the time we're done with the demos. And if you don't know why this diagram is mid, you will by the end of the cohort, and you'll think it's funny too. Okay? I promise. It is funny, but you got to like know. The transformer is funny. It's really funny. I was at a conference last week and they did this. And it was like, this slide is the best slide ever, isn't it? Please never show this slide or this one. It's just confusing and dumb and wrong. Okay, we're going to have you read the paper. And it's important because the details matter here. Okay, let's look at a couple lines in the paper. The dominant sequence transduction models are based on complex recurrent or convolutional neural networks. Well, that's a mouthful. Okay, sequence transduction, that's an important concept. Recurrent neural nets, that's an important concept, especially for NLP. Convolutional neural nets, that was more for images, but you could use, obviously, multimodals and starts to get kind of crazy. But I would focus here on sequence transduction and recurrent neural networks. That include an encoder and a decoder. Interesting. The best performing models also connect the encoder and decoder through an attention mechanism. Attention is all you need. We propose a new simple network architecture, the transformer. One of the best names ever, based solely on attention mechanisms, indicating that maybe previous things weren't based solely on attention. And generalizes well to tasks. Indeed, it does. Okay, there's a couple things I want you guys to know heading into the rest of the week. One is you can do a lot of stuff with the transformer. If you look at a classical transformer, you see things like language translation. That's not generally how we think about it now, but that's a good way to think about the transformer as pictured, because this transformer has an encoder and a decoder. An encoder and a decoder. The encoder kind of tries to understand. The decoder then does the next token prediction. Really, that's sort of kind of, you know, the long and the short of it. Okay? There's a lot of deets. We're going to hit them, just not today. What happens when we understand, or, you know, we're sort of finally standing under, you know, it's like the what's really going on. We fully grokked the sentence and how each word is connected to each other word. We then feed that understanding into here. We'll come back to that. Do we need to do that? And the encoder decoder style transformer is called the BART style transformer. It's good at stuff like translation, which is why we saw that in the pick. BART, you say? That means bidirectional autoregressive transformer. That means it has an encoder and a decoder. The encoder gives us this nice bidirectional, and the decoder gives us this nice autoregressive. So the BART style is this, which ChatGPT is not BART style. The BERT style models are about that understanding of the input. What is BERT? Well, we see this bidirectional. Look at this, encoder representations from transformers. Okay, that's, again, we have a couple keywords, bidirectional and autoregressive. BERT style means this. Now, fun fact, nothing sort of pops out of the BERT style. We have a representation, we have to put some sort of head on it to use it for something. Typically, that's a classification head. There's lots of things we might use BERT style models for. We'll talk about all of those in the weeks to come. Just know that it all comes out of this Ridge paper, right? And then the third one, the big daddy, the one that's sort of one, is the autoregressive, decoder only, GPT style transformer. And they said even back then, it was like, this would be pretty dope at chatbots. Indeed. GPT, okay. Autoregressive. You guys should spend some time thinking about that word. Why would it No one did say that. Auto-regressive. GPT style looks like this, as we know. And we're going to walk through each and every part of the transformer because we just talked about the big blocks. We didn't even look at the little blocks. We didn't look at multi-head attention or single head attention down in there. We didn't look at add and norm. We didn't look at feed forward. We didn't look at linear. We didn't look at softmax. We didn't look at input embeddings. We didn't look at positional encoding. We didn't look at any of this. We just said encoder decoder. We will, but not today. We go deeper. When you're at sort of the top of the transformer, you're sort of doing the next token prediction. What's happening is we're picking the most likely next token based on our understanding of the input, based on what we paid attention to. And there's some probability distribution that we're sort of generating with our generative pre-trained transformer. And we're picking the most likely token in the distribution. That is the most likely token to go next, given our understanding of the input. And, you know, it's like, well, we want it to be kind of probable that it would go next, right? Now, we don't want it to be like infinitely probable, the most obvious possible word. We want to add like a little bit of spice to it, maybe. But generally, we want it to be low surprise to see the next word. Although sometimes, you know, a little surprise, somebody busts out some sick vocab, that adds value, right? So instantly, we're in this nice creative space off the bat, just thinking about how these things work. Going back to the beginning of the game here, when GPT models really started to gain some traction, that was when OpenAI was coming up in the game. In June 2018, GPT came out, they wrote their first blog, and they said, man, when we do this unsupervised pre-training, it makes everything pretty good. And the supervised learning on top just is like, boom, instant dopeness. Because they were trying to do all these tasks like question answering, and sentiment analysis was going well. They did this thing called the sentiment neuron in 2017, and it worked pretty well with just this pre-training, this unsupervised pre-training. And we'll talk about exactly what unsupervised pre-training means and what some of the precursors were in the course. So you see the sentiment neuron was doing pretty good, you know, relative task performance up here. But these other things, they were kind of, you know, they were doing all right, but they were also just doing all right over here, these dotted lines. This is just supervised fine-tuning. So like, you know, linguistic acceptability was just garbage, supervised fine-tuning. Winograd schema resolution, garbage. Question answering, not that bad. Sentiment neuron, pretty good. But when we combine this pre-training with just a little bit of supervised fine-tuning, boom, instantly, we have great performance. And they were like, it's pretty sick. Now it's saying dumb things, and you know, it's like we're not really like, it's not really making sense most of the time at this point. So they kept building. February 2019, they said we scaled it up, kept it going, and we dropped the supervised fine-tuning. Actually, we were able to get surprisingly good results without it completely. And they said simply by prompting the LLM, we could get good results. What kind of results could they get? Let's go to the Wiz to take a look and see. What kind did they get when they said they were pretty good? Simple prompting.
Yes. Okay. So we're gonna go through the ages here of models. Now, it's gonna feel like we went through, you know, years and years, but in reality, it's like, you know, I don't know, 24, 18 months. Okay, so first things first, we've got to ask the classic. We're going to ask all of these the same question, right? Which is, how many R's are in the word strawberry? This is what we care about. The first model we're going to look at is GPT-2, which had extensive pre-training. At the time, it was, you know, it was pre-training, you know, to an absurd degree. Let's look at how it works or how it holds up. So we can compute how many R's in the word strawberry? The answer is, of course, no, the word strawberry. This is an artifact of the fact that it only generates a certain number of tokens. Max tokens is something we're going to get used to over our time together. But as you can see, it doesn't answer the question, right? So the next obvious thing to do would be to create a system that answered questions, right? So we have this, which it just predicts the next token, plops it down, and keeps going on. So it's a good continuing machine, right? But it's a terrible question answering machine, which gets us to MetaLlama, 3.8b instruct. You can see I've already looked at these examples, no spoilers. But this is now a model that has undergone something called instruction tuning. So what happened is that GPT-2 got big enough, became GPT-3, right? And then they discovered that using something called in-context learning, they could get it to answer questions, right? So they could say things like, you answer questions, there's going to be a question, please answer it, right? Show it a few examples of that, a few shot examples, we'll come to know them as, and then it would kind of do the task. But we took that like 15 steps further when we show the model many thousands of examples of these patterns through something called supervised fine-tuning to get really good at this instruction following task, right? So now we can do things like how many R's are in the word strawberry, and we let them count them for you. The word strawberry has 3 R's. We never get back to this competence for many years, hilariously. LLMs used to be quite verbose. They've reduced their verbosity thanks to something we're about to talk about. And so, there you go. So that is instruction tuning. Now we've kind of baked in this instruction following behavior into our models, right? And as Andrew Ng said, if you're going to fine tune a model off the shelf, you should take an instruction tune model. This kind of changed the way we think about or interact with models and has led to what we see today, proliferating at an absurd pace. But then we want to, I think I maybe lost my screen share, so I'll just go ahead and put it back. There we go. Okay. But then we see, the next evolution, which is I want to customize this. I want this to be my, model. And that's where we get to something like Gen Z AI, right? Where we have the ability to personalize these models and retain their instruction following behavior. In this case, AI Makerspace, we fine-tuned this silly but fun example of the Gen Z translator, right? The basic idea is we can give it English sentences and it's going to spit them out in Gen Z language, which is to say, what this looks like, no cap, for real, right? So sorry if you cringed hearing me say that, but the idea is we're able to personalize them. And not only are we able to personalize them effectively, but we can do so with extraordinary efficiency, right? Thanks to techniques like QLoRa, thanks to techniques like, or tools like Unsloth and others that we're going to spend some time covering. We're able to do this with a tremendously small fraction of the compute that the original model trainer used to actually generate the model. So this is the next step, right? So now we're personalizing these things. And this involves some post-training, right? So we go from just instruction tuning. Now we're going to do some supervised fine-tuning on top of that. Maybe we're going to do some alignment. And then we take that to its logical extreme and we get RC Supernova. RC Supernova, which has been not just, it's not just leveraging a pre-trained model that's gone through post-training and instruction tuning, right? Though it has done that. It's also gone through a number of alignment steps, as well as merging steps, as well as, these kinds of newer RLHF adjacent alignment steps. So, RC Supernova has gone through countless examples, right? And then finally, we get to the winner, the absolute king, number one, and that's it. What we'll do is we'll see it work, and we can see it thinks. It doesn't just do now, right? It thinks. We have this thinking step. I'm curious about determining the number of R's in the word strawberry. Careful analysis, letter by letter, securely lead to the conclusion that the word contains 2 R's. And then it comes to the conclusion that there are 3 R's in the word strawberry. So it finally gets there. And that's the kind of evolution, the sweeping evolution of the ecosystem. And we'll return to Greg to learn a little bit more about some of the models we talked about.
Yeah, let's go. So that was years of models in just a couple of minutes here. Let's see if we can recap what we just saw. Now, we heard about scaling laws. If we go bigger, we do better. From GPT-2 to GPT-3, that's exactly what they saw. And they were like, we're kind of worried about this. We should probably align this a little bit better towards what we think humans want. See, because humans, they don't need to see tons and tons and tons and tons and tons of examples of the same thing. Humans just be like, yo, other human, can you go do this thing for me? And they'll be like, yeah, 100%. Got you, bro. Right? Got you. Even little tiny humans, even children. And we want our models to at least be able to behave like this. Now, we hear a lot today about models are like PhD level, which are still, children in many ways, if you ever went to grad school. And this idea of giving instructions, giving clear and specific, that is clear and specific instructions. This is fundamental to prompt engineering. This is fundamental to putting what you want the model to do in context. And there's a lot of other things you can talk about with prompt engineering and putting the right stuff in context, retrieval processes and RAG, and this is where all that comes in. And there's all sorts of interesting things that you could talk about with prompt engineering. But the instruction is the point here. And when we put it in context, we put it into the context window, when we put it into the chat box, when we're having a chat with a chat bot, GPT style, generative pre-trained autoregressive transformer chat, then we see the same behavior that we saw with GPT-1 as we've scaled. Instead of just kind of going on and on and on with this crazy pre-training, turns out if we get our models big enough, the pre-training does really well, 175 billion. And if we give it just one example, just one shot, 0 shot instruction only, 1 shot, 1 example, we get this peak, we get this great performance. And then we go 2 shot, 3 shot, 4 shot, up to 32 shot, I think here. And you get better and better and better and better. Now, as you get better and better and better and more shots, you meet your other friend. You meet fine-tuning. And, you're sort of back to this fine-tuning thing that you just left, okay, when you did pre-training and you ditched it. You ditched it, but now you want it back. You want to put the human's face on it. You want it to follow instructions like us. You want it to align with our expectations. And this idea of fine-tuning is rooted in classical supervised learning. It's supervised fine-tuning, after all, different than the reinforcement learning with human feedback or other methods. And, when we do this kind of prompting, and we go far enough down the number of examples, we go far enough down the optimization spectrum. How many examples towards this task am I going to give it? This is called the task-specific spectrum. I do 1 shot, I do 0 shot, I do 1 shot, I do 2 shot, 3 shot, 4 shot, 5 shot, 10 shot, 100 shot, 1,000 shot, 100,000 shot, synthetic data generation, million shot, maybe next year, right? We want it to be really good. Then all of a sudden, what am I doing? Well, I'm fine-tuning again. So it starts to get real crazy. Like, I thought we ditched fine-tuning, but now we want it back, and there's all this stuff. And, the prompting kind of pulled us out of the model. But when we go far enough down the task-specific spectrum to try to get it to follow instructions, to try to get it to do specific tasks, then we kind of put it back into the model. So there's a lot of cool stuff going on here, but in the end, we want the LLM to act in a certain way, right? When we want to give it a bunch of examples, we want it to act in a super specific way. There's lots of ways you can get it to act that we'll talk about in this class. Today, the one you saw, the Gen Z AI, is an example of language training, where we just took some data, some simple Gen Z definitions, and we created synthetically a data set, question, answer, question, answer, question, answer, and we taught it the kind of behavior that we wanted. We took a model off the shelf, we gave it these pairs, took the instruct-tuned model off the shelf, as he mentioned, always pick the one that follows instructions well and then fine-tune it. So we dropped fine-tuning, we started instruction tuning, and then we aligned it, and then now we're doing more fine-tuning. We're just teaching LLM exactly how we want it to act. And again, there's a big chasm between Gen Z AI and the kinds of things that we see today. The 70 billion parameter models, the distilled models. When we see the 405B instruct again, right? We see the instruct and it's distilled, but then also they fine tune a few other LLMs and they line another LLM, they merge them all. And then, like, what exactly is going on in the biggest, beefiest, longest test time compute model, O1? That still is getting the strawberry question, although, it's doing it, it's thinking it through. What's going on there? What are these large reasoning models, these LRMs, right? What are they? All of this is important to ask these questions. And all of this is the kind of thing that by the end of this course, you will have deep insight into. As we conclude, I want to spend a little bit of time walking through what we're going to ask you to do over the weekend. What we saw today is that LLM engineering is a set of emerging best practices for pre-training, for post-training, and we didn't talk about it much, but for optimizing LLMs prior to production. Importantly, we have tools that you guys need to become familiar with over the next few weeks. And homework for Tuesday is to read Attention Is All You Need. If you want to go talk to Wiz about it, he's available tomorrow, 3 p.m. PT in his office hours. And so here's what we want to do with you guys right now. Let's take a look at this paper. And the homework is to read the paper. Let's walk through what the most important things here are. So Wiz, if you could join me here for a moment, like, is all of this thing important or is it garbage? I mean, we did the abstract already. Some keywords like sequence transduction, like recurrent neural nets, encoder and decoder through an attention mechanism. Okay, check. As we move on here, what jumps out at you, Wiz, as particularly important? I think the background and context is interesting, especially for those with a machine learning background, especially for those that have studied deep learning and studied LSTMs and recurrent neural nets and more kind of rare versions of them. And then to sort of try to understand how things like that used attention, didn't exactly only use attention, is particularly interesting. Anything else jumping out at you, Wiz, here? Let's see.
We're soon getting to the part that's gonna jump out at me. For sure.
So it's it's like this is not codable stuff yet, guys. Okay, so notice he doesn't care. I care about the context. So pick your own adventure here, right? Here we are, model architecture. Okay, this tells us the kinds of things, and we there it is, the beauty. Look at this guy, what a beaut.
Good diagram.
I understand the transformer. I read the paper. We're done, right? Okay. No, I'm just kidding. But for real, that's how people behave. All right. So encoder and decoder stacks.
Yeah,
here.
This is the one.
Oh, okay. Now we're getting into
stacks, right? So when we're when we eventually start exploring this more and more, we're going to realize what a powerful word stack is, right? And we're going to see how powerful that n equals 6 or n equals x is. I think that's something that's going to become extraordinarily important on our journey.
So we have sublayers, we have regular layers, we have stacks. Okay. We got the decoder doing the same deal, right? Now, I like this last line here, talking about masking, particularly note this masked multi-head attention up here versus multi-head attention, quite important. The masking is the secret sauce there. Okay, let's keep rolling in the interest of time. Oh, we got these other beauties. Okay, duh. Yeah, I get QKV.
You gotta
dot product attention, right?
You gotta know the math here. Relate dot product attention to dot product, relate dot product to cosine similarity to get a kind of intuitive understanding of, why something like this is working under the hood.
Scale dot product attention, zoop, that's there, right there, boom. Then we're in the multi-heads. So, wow, we got some math here, yikes. Softmax Q times K transpose over the square root of the dimension sub K. It's getting rough already. Let's see, 56. Okay, so just kind of scrolling through a little bit quicker here. This is important, and I would highly recommend you guys check out the illustrated transformer. Again, if you dig into the transformer materials we have on the homepage, you'll see a lot of supplementary materials with visualizations. Multi-head attention. You kind of can't understand this unless you understand the attention first.
And I think this is where we start to enter optimization world, right? When we think about things like multi-head attention, when we think about the way that our hardware is set up to do these computations, think about ways we can potentially split these operations either across hardware or across different parts of memory. This is where some of that intuition is going to start to get rolled in.
Oh my God, and look at that. We're on page 5 out of 15, and we're out of time. Classic transformer. Oh my God. Okay, so that's what it's like to study the transformer in short right there, guys. So go ahead again, first once through. We're going to continue to layer in and stack in and decode everything in there for you.